Okay, let's continue our discussion of Section 8.1. We have just a little bit left to go. And so we were just reviewing the idea of the mean of a binomial distribution being very easy to find by just taking the number of times that our specific situation is going to take place and then the probability of a success. And we can find what the variability will be by taking the square root of n times p, which is the number of different outcomes times the probability of success times the probability of a failure. Now, if we graph a distribution, a binomial distribution, we're going to find that sometimes the distribution will actually look quite bell-shaped. For instance, if I went to our scenario that we were discussing, and I've already gone ahead and put in my inputs the 0 through, and remember we had 15 people who were being selected, and we had a 30% chance of somebody being Hispanic. And I'm going to actually graph the histogram of this situation. So I have values in here, and I think I need to add a few more. I need 11, 12, 13, 14, 15. So if we were making the entire probability distribution for our scenario, we would have 0 through 15 as the number of Hispanics who could be chosen. And if I go up here to list 2, and I'm going to put in a formula to find the probability, and I'm going to go to my second in distribution, and I'm going to go to the binomial PDF. Now I know I have 15 different people who are going to be chosen. Each person has a 30% chance of being Hispanic, and I'm going to let the number of Hispanics people be list 1. And that's going to actually figure out and calculate my entire probability distribution. So that just figured out 16 probabilities for me real quickly. Now I'm going to look at that graph. And before I set up a little window, I'm going to kind of look through here and see. It looks like the highest number for the probability looks like it occurs when you have 4 people being chosen, and which is real close to what the mean is. So I know I'm going to have my window go up to at least 0.22. So let's set the window. I'm going to have the window go from 0. The highest number was a 15, but I'm going to have that go up to 16 going by ones. I'm going to have my probability, my y value start at 0. I'll go up to 0.25, scaling by 0.05. Just a second, I have to cough. Hopefully that wasn't too loud. And let's see a graph. I'm going to check my y equals. All right, so let's turn a stat plot on. Got a little histogram here with the frequency of list 2. Excuse me. And that graph looks quite bell-shaped. Now, is it symmetrical enough and having the 68, 95, 99.7 rule, do we have enough information to say that this is approximately a bell-shaped curve or a normal distribution? It looks pretty close, but we need a way of not just eyeballing it, and this is the criterion that we'll use. If we have a binomial situation, and if we take the probability of a success times n, and that would tell us how many successes we expect to get, n times p, that's the expected number of successes. And if we take n times 1 minus p, that's the expected number of failures. If both those are at least 10, statistically we find that our bell-shaped curve will approximately occur when we graph the histogram. So for our setting, we knew that n times p was actually equal to 4.5. So what that would mean is, since that's smaller than 10, although the graph of our distribution, our binomial distribution, looks pretty bell-shaped, we actually don't have enough bell-shaped, and that 68, if you add on 1 standard deviation to the mean, you won't have approximately 68%. If we add on 2 standard deviations, we won't have approximately 95%, and so on. So this is quite close to a bell-shaped curve, but we actually would not say it is approximately normal. And that real fast test is, again, your expected number of successes, which is n times p, and your expected number of failures is n times 1 minus p. Both those need to be at least 10 for us to use an approximate normal distribution. So let's look at an example. If we had, and I have a little game situation here, suppose that we were playing a game of chance where we had a 30% chance of winning. So similar to our Hispanic situation, 30% chance of a success, and you play the game 100 times and keep track of the number of wins in 100 games. And I said find the distribution in your calculator. Well, we could very easily again go in here and put down our numbers from 0 to 100, and we could have the distribution of binomial PDF, and having our number of times we're playing the game is 100. The probability of success is still, we have a 30% chance, pretty good chance of winning. And we can put in our list 1 here. And again, I would have the numbers from 0 to 100, although I know my expected number of wins is only 30. So even though I might put in my distribution to go all the way up to 100, I really don't expect to have very many values up at 100. And I know that my expected standard deviation of that number of wins is only going to be 4.58. Now, if I go through with this distribution and I get all of those probabilities, it will take quite a bit of time. I'll find out that it's not a very good chance that I win 0 or 1 or 2 and so on. Now, I found that you have about a 0.2% chance of winning 18 games out of 100. You can see I've skipped some. I have about 2.8% chance of 23 games being won, and etc. And very, very small chance of winning all of them. And I'll leave that for you to graph that on your calculator. But when you graph that distribution, it actually is approximately normal. Why? Because n times p is 30, and n times 1 minus p is 70. And since both these numbers are larger than 10, our graph of our histogram for that binomial distribution will actually be very, very close to a normal distribution. So much so that we can actually do some normal calculations if we're trying to find, say, what's the chance that you win 35 or more games. So we'll do some other examples of that where we'll actually use normal calculations as opposed to binomial calculations in a couple of exercises that we have. So that's it for this tape.